This is power. As you probably remember from last year, power is the rate at which work is done. The units of power are watts, capital W, and 1,000 watts is equal to 1 kilowatt of power, little k, capital W. The equation itself is fairly straightforward. Because it's a rate, it's work done over time. So the average power is equal to work over the change in time, something you should probably already know. All right, next step. Let's see if I can get this to work. There we go. On page 212 in your textbook, there is an equation for instantaneous power. This equation is also found on your AP equation sheet. This is something you should know. So the instantaneous power is equal to the force applied times the velocity and the cosine of the angle between the force and the velocity. This is a less common form of power. And example 6.13 on pages 212 to 213 illustrate the use of this equation. It's basically a car going up an incline or up a hill, and they go through a lot of detail on how to solve this problem using the angle and what the relevance of having that angle is. And so I'm not going to go into detail because your book does a really good job explaining how this equation works. But this is one you should know. Now, example problem. Let's do power here. A 40 kilogram object experiences the force shown on the graph, this graph right here, for a total of 8 seconds. Determine the work done, the average power, and the final velocity of this object. Now what I want to do is kind of break it down first, looking at what we know and what we need to find out in order to get this stuff. Again, this is a force versus displacement graph, and we'll take it from there. Okay, the work done. The relationship between force and displacement, you probably know that the work is equal to F times X, but if the force is changing, in other words, if this graph has a diagonal line, it's much easier to calculate the area under the curve. Area under the curve is work for a force versus displacement graph. Of course, I think you guys can probably do triangles and rectangles, but let me just shape it out here. So you have a series of well, basically triangles and squares. They're not necessarily rectangles, just coincidence here. So 1/2 10 times 10 is going to be 50. That's region 1. Break down the regions here. Region 2, 10 times 10. You don't need a calculator for that one. Region 3 is another 10 by 10. Region 4 is 10 by 10, but it's a triangle. So you're going to get 50. Region 5 is 20 by 20. And that should be 400. Region 6 is 10 by 20. Half of that is going to be 100. So when I add them up, let's see, I get 150, 250, 300, 700, 800. 800 joules of work. Okay? Add up the areas. So part A, the work done is 800 joules. And hopefully you didn't need a calculator for that. Now the average power. As you know, average power is equal to the work done over the change in time. Well, it's already given that the time is 8 seconds. We just determined that the work done is 800 joules. And surprise, the numbers are nice, aren't they? Average is equal to 800 over 8, and that would be 100 watts of power. Again, this is fairly straightforward, but it's good to remember this stuff. Now, final velocity. This is one where you know how to do this if you just stop and think about it for a minute. Work is a change in energy. You know this. Now, what type of energy is changing? What type of energy is changing when you apply a net force? A little quick pause. I feel like I'm Dora the Explorer. There it is. It is kinetic energy. Okay? If the k is increasing, the velocity is increasing. So we can assume that the work done is the change in kinetic energy. Let me scroll down a little bit here. Now, in the problem, we were given that the mass was 40 kilograms, right? And we know that the kinetic energy is 800 joules. So let's set it up. K is equal to 1/2 mv squared. 800 is equal to 1/2 40 times v squared. Half of 40 is 20. 800 divided by 20 is equal to v squared. V squared is 40, and I'm pretty sure that's going to be like 6.3. Yeah, probably something like that. Let's get that calculator up here. There you are. So let's do 40. Where's my square root here? There it is. 6.3. So if we understand that the work done is changing the kinetic energy, we can use this equation here to determine the final velocity. Of course, another extension might be what was the acceleration, or something that involves the four equations. That might be a good extension to this problem. All right, so let me get over here. I just realized that I lost my little icon for the video recorder. All right, that's it for power. Thank you.